All right, today we are diving into one of the most fundamental rules in the entire universe. Seriously, it's a principle that governs everything from how stars burn to how the phone in your hand actually works. So let's get into it.
But first, let's start with a huge question, one that has kept inventors and dreamers up at night for centuries. Can we build a machine that runs forever? A perpetual motion machine that just powers itself, no strings attached. It's an amazing idea, but to really understand why it's impossible, we first need to talk about energy.
Because absolutely everything, and I mean everything, runs on energy. The best way to think about it is like a universal currency. It's what you spend to make your car go, what your body burns just to keep you alive, and what a power plant uses to light up an entire city. Nothing, and I mean nothing, happens without an energy transaction.
But here's the thing, this currency isn't just a free-for-all. It's governed by one single, totally unbreakable golden rule. And understanding this rule is the key to understanding, well, pretty much everything. And here it is, the first law of thermodynamics. This is the ultimate statement on conservation of energy. It means you can't just make energy out of thin air, and you can never truly get rid of it. All you can ever do is change its form. From the chemical energy in gasoline, to heat from the explosion, to the kinetic energy that actually moves your car, the grand total of energy in the universe, it always stays the same. Now, what's really cool is that we can take that huge, profound idea and boil it all down into a simple but incredibly powerful formula. And this isn't just a bunch of math. Think of it like a cosmic accounting system for all the energy that exists. This is it. Delta U equals Q minus W. It looks almost too simple, right? But this little equation lets us track every single bit of energy in any process, making sure none of it ever magically appears or disappears. So, what on earth do these letters actually mean?
To really get this equation, we need to meet the three key players on the stage. That's internal energy, heat, and work.
So first up is U, which stands for internal energy. The easiest way to think of this is like the system's energy bank account. It's the grand total of all the energy, all the jiggling and vibrating of all the molecules locked up inside whatever it is we're studying. And that little triangle, the delta, that just means the change in the account balance. Simple as that. Next, we have Q, which represents heat. Now, this is energy that's on the move, always flowing from something hotter to something colder. In our bank account analogy, adding heat to a system is like making a deposit. You're adding funds, you're increasing the balance in that energy account. And finally, there's W for work. This is energy that's leaving the system to go and do something useful, like a hot gas expanding to push a piston in an engine. So, what is this in our analogy? It's a withdrawal. You're spending some of your internal energy to make something happen in the outside world. Of course, for any of this accounting to make sense, we need to be really clear about what we're studying, what scientists call the system. An open system, like a pot of boiling water on the stove, can exchange both stuff, matter, and energy with its surroundings. A closed system, like a sealed water bottle, can only exchange energy. And then you have an isolated system, like a perfect thermos, which, in theory, exchanges absolutely nothing.
And just like any good accountant, we use positive and negative signs to keep track of the flow. So when heat Q is added to the system, we call that positive. It's a deposit, right? And when work, W, is done by the system, like that piston moving, we also call that positive because it's energy leaving to do something useful. That's why the W is subtracted in our formula. The change in your bank account is the deposits minus the withdrawals.
Okay, so that's all the theory. But let's see how this law actually plays out in the real world. This is where it really starts to click. So check out these two really important special cases. Over on the left, you've got an isolated system, our perfect thermos. Nothing gets in, nothing gets out. So Q and W are both zero. That means the change in internal energy, delta U, has to be zero too. The energy inside is just constant. But on the right, you've got a cyclic process, like an engine's piston, going up and down and back to the start. Since it ends where it began, its internal energy doesn't change overall. In that case, all the heat you put in has to come out as work. Q equals W. Now, I know this can feel a little abstract, a bit like a physics textbook, but I promise you, this law is the absolute foundation for so much of the technology that defines our modern world. So why does it actually matter in our day-to-day lives? Oh, it's everywhere. Your car engine is literally a machine built around that Q equals W principle, turning heat from burning fuel into the work that gets you down the road.
Cooking, that's just adding heat Q to increase the internal energy U of your dinner. A refrigerator is even cooler, no pun intended. It does work, W, to pump heat out of the system. And every single power plant on the planet is just a giant, magnificent testament to this law, transforming one form of energy into another. But, and this is a big but, for all of its incredible power, the first law has a huge blind spot. It perfectly balances the energy books, it tells you that the totals all add up, but it doesn't tell you why things happen in a certain direction. For example, it doesn't explain why your hot coffee always cools down, but you'll never see a cold cup of coffee spontaneously heat up by pulling energy from the table, even though that wouldn't break the energy conservation rule.
And that brings us to the big final question. The first law says energy is always conserved, but we all know from experience that energy seems to, well, it seems to spread out, to become less useful. That car engine isn't 100% efficient. A ton of that energy just becomes useless waste heat. So if energy is never truly lost, where does it all go? Well, my friends, that is a fantastic question for the second law of thermodynamics.